So we are briefly going to review what we had done so far. We are looking at thermodynamics, and we said that if I want to describe a system, then I need to describe it in terms of a set of macroscopic variables, and these macroscopic variables are essentially of two kinds. They are intensive or extensive. The intensive ones we understood are the forces Fi, and the extensive ones are the ones which we understood to be the coordinates xi. And then, using the analogy of mechanics, we wrote down the work done as Fi dx sine with a sum over I. The first law, the zeroth law, of course, comes into play in saying that I can define a temperature, an empirical temperature, therefore I can pick up isotherms in the PV or in the coordinate space. Similarly comes the first law that tells you that d cut q is equal to du minus d cut w. The cut means it's an inexact differential, that is, the heat and the work depend on the path taken. Once again, the path, we clarified what does the path mean. Path means essentially the trajectory of the thermodynamic system in the coordinate plane. So this path would be typically the path that is taken in the force and the coordinate plane. So xi and fi. So fi, which is the force, is conjugate to the coordinate. So this can be like this, this can be like this, this can be like this. It goes from state to A to B and then B to C, something like this way. Then enters the second law, which tells you that ds must be greater than equal to d cut q by t for any process. If it is an irreversible process, then I know that the equality holds and write down d cut q by t as ds, which modifies the first law as tds is equal to du minus d cut w. And this is the statement of the second law. Yet another statement of the second law tells you, or not a statement of the second law, but this is a consequence of the second law. This rather is the statement of the second law. What it also particularly tells you, that if you have an adiabatic system and if the subsystems which were in equilibrium come to a joint equilibrium, then you know that ds must be greater than equal to 0, which effectively means that entropy must be maximized for an isolated system. This means that if you have an isolated system and if you take the system out of the equilibrium, then it goes to the equilibrium state. It should go to the equilibrium state by maximizing its entropy. Right? The most common example that you can visualize is that you have a can of gas or a liquid and you cool the liquid. You put it in the freezer so that it comes to kind of an equilibrium, which is a different equilibrium, and then you bring it out. So you have a liquid and which is at a lower temperature. When you bring this liquid, this can of liquid from the freezer and set it outside, then it is at a lower temperature than the ambient temperature. The ambient means the surrounding temperature, then you know that the temperature of the liquid rises, and thereby, since the temperature of the liquid rises, things becomes more mobile. So this also molecules also start to move more vigorously, and therefore the entropy increases. We shall later on look at these things. This also means that any spontaneous change, if you have an adiabatic system, any spontaneous change must lead to a maximization of entropy. So perhaps this was a very not such a well suited example. If you can imagine that you have a can of gas contained within an adiabatic walls, and then you press, there's the top part is a piston, you press it below so that it gets suppressed. But this is not a spontaneous change because you have supplied energy. This means a spontaneous change would mean that there is a spontaneous change within the system that would lead to the contraction of the volume. That is not allowed because that is a decrease in energy. Any spontaneous change can lead to an expansion of the volume, right? So then comes the fact that now that we have introduced entropy, we write down the entropy as a function of the internal energy and the generalized coordinates, or in the internal energy as a function of entropy and the generalized coordinates. You should note over here, for example, if you just look at this, so these expressions that we have seen are the fundamental equations of type 1, and this is the pillar of thermodynamics. If you know these relations, then it gives you everything. The limitation of thermodynamics is that these equations must be given to you. You cannot derive them. Statistical mechanics, on the other hand, tells you how to derive them. So we shall see how to do that when we do statistical mechanics. Now, coming back to this, if you see, I have written down internal energy as a function of entropy and the generalized coordinates. This need not be true, in the sense, so okay, let me first see what I try to say, that your internal energy, it may not be that it's a function of all the thermodynamic coordinates, the extensive variables. I can replace any of these thermodynamic variables by its conjugate force, F1, X2, Xn. I can define some thermodynamic free energies, let's say U1, U2, S, X1, F2, so on and so forth. So you can see that there are various possible combinations that are possible. So I can replace the coordinates by their conjugate forces and define a new thermodynamic potential. So that is allowed, right? For example, you can look at Helmholtz free energy, right, or Gibbs free energy. So once you know all these functions, then clearly you can write down ds as del s del u. The xi's are held constant, du plus sum over I del s del xi, u and xj not equal to xi are held constant, dxi, and similarly you can also write down du as del s del u del s xi are held constant, ds plus sum over I del u del xi, s and xj not equal to xi, dxi. Recall that both internal energy U and the entropy S are state functions. which means u and s are state functions. This means they do not depend on the path. In other words, these are what are called exact differentials. And the property of the exact differentials are such that you can write down the differential form if u, let's say, if u, okay, we will not write down u, so we will consider any arbitrary function f, which is a function of x1, x2, xn. So this is an arbitrary, it's a function. Then if it's an exact differential, I can write down del f del xi dxi. So you can clearly write down this for u and s, and therefore we wrote down the earlier forms that you could see. When you look at, so when you deal with a thermodynamic system and you write it down in this, you start off from this relation, you are doing the energetic formulation or internal energy formulation of thermodynamics. If you rather do it like this way, you are doing the entropic formulation of thermodynamics. Both are valid descriptions, there is no difference between them, and we have seen earlier also that this relation delta S must be greater than 0, or in its differential form, let's say ds is greater than equal to 0 implies that du must be less than 0. So maximization of entropy is equivalent to minimization of u, and the reason for this is basically that the temperature is a positive quantity, and the temperature is a positive quantity is a consequence of Kelvin statement. It's a consequence of second law, which tells you that you cannot have a negative temperature, right? So once we know this, u and s both have another property which is very interesting, which is also very relevant. So we want to just list down the, so u and s are exact differentials. Delta s greater than 0 implies or is equivalent to delta u less than 0. Further, u and s are extensive quantities. What does this mean? So let's look at a system. Let's take a system, big system we can imagine, and let's divide this into subsystems, right? So what we say is that there are lambda subsystems that make up the whole system. Now, each of these subsystems the entropy is S, volume is V, and particle number is N. So this means that if I want to find out what is the value for the whole system, the obvious is lambda V and lambda N. And the extensive property of the entropy means that the entropy is additive, so it is lambda S. But the extensivity property of U, what does it mean? That if this one has U, this one has U, this one has U, then the whole system should have the internal energy U. So let me repeat my argument again here if you have just missed it out. Let's look at the system which is made up of lambda subsystems. This looks a little ugly, so let's just draw it properly here. Yeah. So each of these subsystems have S, V and N. This is a hydrostatic system we are talking about. So I have a gas which is contained in a container, and I subdivide the volume of the whole container into lambda subsystems. Each of these subsystems have the entropy S, the volume V and the particle number N. Then my question is, what is the value of SVN for the whole system? Well, the two obvious answers for V and N I know. I will simply add up the volume and I will get the volume of the whole system. I will simply add up the particle number for each of these subsystems, and then I will get the whole the particle number for the whole system. Now comes the entropy. What happens to the entropy? The extensive property of the entropy implies that they are additive, which means that if this system has an entropy S, this system has an entropy S, this system has an entropy S, then I simply keep on adding the entropies to find out the total entropy. U is also extensive, that's the property that we are trying to say. Then it also means that the internal energy are also extensive quantities, so I will simply add up. Therefore, the internal energy of the system becomes lambda times T. On the other hand, the entropy of the system, whole system, becomes lambda times S, volume becomes lambda times V, and particle number becomes lambda times N. Therefore, if I write down this equation, lambda S, lambda V, lambda N must be equal to lambda times USVN. Correct? So this means that the internal energy of the whole system, which has an entropy of lambda S, volume of lambda V and particle number of lambda N, would be simply lambda times the internal energy of each of these subsystems. Functions which obey such a relation are called homogeneous functions. Okay. So before we want to understand what homogeneous functions are, what we want to write down is, let's choose lambda is equal to 1 by n, right? Then it follows u of s by n, v by n and 1 is equal to u by n. So therefore, you see the number 1 is not very important. So if I define small s as capital S over n, small v as capital V over n, then u of small s and small v is u by n, right? So the homogeneity property allows me to define densities. You could have started the argument in other way around. You could have said that, look, my system has an internal energy U, volume V and particle number N. So subsystem. Therefore, what is it for the total system? And you could have carried it out for the whole system, and you would have come up with the relation that lambda U, lambda V and lambda N must be equal to lambda times S U V N. And again you would have done the same procedure, then you would have defined the entropy as this. So it's a homogeneity property of the internal energy and the entropy that allows you to to define densities for these two quantities. Remember, we are talking about internal energy here. You can do it for any extensive quantity. For example, for any free energy can also be defined in terms of densities, because that's a property of it, because it's a homogeneous function, right? So what does a homogeneous function mean? Mathematically, if I have x1, so once again I consider a function of many variable and I write it down in this way. So it's lambda to the power k xn. If a function obeys such a relation for arbitrary lambda, then this is called a homogeneous function of degree k, right? This is the mathematical definition. One can take a derivative with respect to lambda on both sides. If I take a derivative with respect to lambda, then basically del f of xi del lambda xi times xi, this is just manipulating the derivative on the left hand side, is k lambda k minus 1 f of x1 xn, right? This is what is called an Euler relation. It obeys, any homogeneous function must obey an Euler relation. Now if you put lambda is equal to 1, which you are allowed to do because any arbitrary values of lambda are allowed, then it means that sum over xi del f del xi must be equal to k times f xi. It is understood that this is a function of okay, let's just see, all of this particular relation follows from this relation, right? And there is nothing cleverness or nothing ambiguous about it. If a functional relation, if a function satisfies this relation, then it must satisfy this. But now I know my internal energy obeys this particular relation, and this is strikingly similar to this particular the relation that you see over here with k equal to 1. If this is the case, then I will also have a similar relation over here. So let's write down the Euler form or the Euler relation for this. So this means it is a function of s, v and n. Therefore I should have, if I write down explicitly, u must be equal to the right hand side s del u del s. The rest of the xi's are fixed, which I am not going to write. It's implied that they are fixed. V del u del v plus n del u del n. Correct? But what is u del u del s? I know that del u del s from the first law is equal to t, and del u del v is equal to minus p, right? If you have forgotten how to write it down, you always write down the first law for the hydrostatic system, p dv minus mu dn, and then you can see that del u del v is minus p and del u del n is equal to mu. So let's write down, this means that ts minus pv plus mu n. So if I combine this equation with the first law, together with the first law, I come up with this particular relation. Now I want to take a differential of this equation. So write down du. Du would be t ds plus s dt minus p dv minus V dP. Here, when you write down the differential in U, you allow for all the variations of the thermodynamic variables. There is no restriction. Plus mu dN minus n d mu, which I can simply collect terms together plus S dt minus V dP minus n d mu. Remember your first law, if you now look at your first law, you have exactly this. The left hand side du cancels with the right hand side, the three terms in the right hand side. Therefore, you see S dt minus V dP minus n d mu must be equal to 0. This relation is called Gibbs-Duhem relation. It is surprisingly simple, but it is very, very powerful. See, if you look at the first law, which is this one over here, then if I want to vary the generalized coordinates, I cannot vary it arbitrarily. I mean, their variations are constrained. V and n are constrained, right? So if it's an adiabatic wall, then du plus pdv minus mu dn must be equal to 0, right? So in the first law restricts the variations or constrains the variation of your generalized coordinates. If you look at the Gibbs-Duhem relation, it does opposite that. It restricts the variation in your generalized forces. T is conjugate to the entropy, which is an extensive quantity and therefore a thermodynamic coordinate. The conjugate force is the temperature. So the Gibbs-Duhem relation does nothing but it restricts the thermodynamic forces. So you cannot arbitrarily vary T, P and mu. You can arbitrarily vary any of these two, but arbitrarily you cannot do that. So if you fix T, if you fix P, then the chemical potential is also fixed. The Gibbs-Duhem relation, now, okay. What is also interesting to note is that this is nothing but a consequence of the homogeneity property of U. If U was not extensive, it wouldn't be homogeneous, and therefore you cannot write down this. You cannot write down a Gibbs-Duhem relation if you say U was an intensive variable. Temperature is an intensive variable, therefore temperature is homogeneous of degree 0, that is kappa is equal, K is equal to 0. Okay, so I'm sorry, this has to be plus. This has to be plus. Please rectify, I missed the sign over here. So we did it with the internal energy. One can again do it with the entropy, where I have UVN and I know that S of lambda U, lambda V and lambda N must be equal to lambda times S of UVN. So therefore, if I want to apply the Euler relation over here, this would mean that S, because it's a homogeneous function of degree 1, S is going to be del S del U times U plus del S del V times V plus del S del N times N. Please note that there are quantities which are held fixed, which I am not writing explicitly, but it should be obvious to you. But del S del U is U over T. Sorry, the del S del U is 1 by T, therefore this is what you get. And then del S del V is minus P over T, right? Del S del V is plus P over T, sorry. Because if you write down T ds is equal to du plus P dV minus mu dN. And the pressure is defined as the force which is conjugate to the volume is defined as minus P. and then you have minus mu over t arbitrary. If you carry out the differential, then this means du 1 by t plus u d of 1 by t plus p by t dv plus I want to write down v d of p by t. There is minus mu by t dn minus n d of mu by t. Look at this term, and this term. Together they form the first law. So therefore you are left out with the variation just getting a little bit sloppy here, plus v of dp by t minus n d of mu by t must be equal to 0. This is the Gibbs-Duhem relation in entropic formulation. Entropic formulation would mean that you have started off with entropy as with the fundamental relation where your entropy is a function of u and the coordinates, and an internal energy formulation would mean that you have started off with the internal energy, the fundamental equation of type 1, where internal energy is just a function of entropy and the coordinates, right? So you might wonder that why are we restricting ourselves to u and s? What we are always trying to talk about here is an isolated system which is not connected to any kind of environment. So you do not have a bath. So we will come to that later on, how to treat such systems, because in reality we do get the environment. Whenever you do experiments, it's coupled to the surrounding. But we are typically talking about the isolated system where the entropy is the only as a function of UVN, or the internal energy as a function of SVN are the quantities of interest. So now I have u of, again, so u d of 1 by t plus v d of p by t minus n d of mu by t is equal to 0, right? Let's see how strong or how powerful this equation is. So I want to apply this for an ideal gas. I want to see what the ideal gas gives me. This also gives you the third equation of state if you know only these two, right? So if I have PV is equal to NKBT and U is 3/2 NKBT, right? Then P by T is equal to NKB by V, and U by, so 1 by T is equal to 3 by 2 NKB by U. Let us substitute over here. Then I have D of 3 by 2 NKB over U plus V D of NKB over V is equal to N D mu over T. Okay, so let's do the differentials now. U 3 by 2 NKB d of 1 by u is minus du over u square. So this term multiplies this term plus u 3 by 2 kb by u dn plus v nkb multiplying minus dv over v square plus v nkb, shouldn't be n here, kb over v dn is equal to n d of mu by t. Let's simplify. It's a little bit of an algebra, but it's doable. So this tells you minus 3 by 2 nkb du by u plus 3 by 2 kb dn plus, so again we will have a minus sign because of the derivative. We will have minus nkb dv by v plus kb dn is equal to n d mu by t. Divide throughout by n. If I divide throughout by n, then I have minus 3 kb, 3 by 2 kb du by u plus, there's a 3 by 2 kb over here and there is a kb over here, that makes it 5 by 2 kb dn over n minus kb dv over v is equal to d of mu by t. I can take care of the kb also, so what I will do is I will simply write it down like this way, plus 5 by 2 dn by n minus dv by v is d of mu by kb t. So that the right hand side becomes a dimensionless thing. Look at this equation now. If I look at this equation, then the left hand side I can write down as n to the power 5 by 2 v times u to the power 3 by 2 must be equal to d of mu by kbt, which means mu over kbt is n to the power 5 by 2 v u to the power 3 by 2, and there is an arbitrary constant which I put it like this way. So sorry, there is no. So look at this equation now. Then the left hand side is 5 by 2 d of ln n minus 3 by 2 d of ln u minus d of ln v is d of mu over kbt. So which means I can write down this as d ln n to the power 5 by 2 by v u to the power 3 by 2 is equal to d of mu over kbt. So it follows mu over kbt is equal to ln kappa n to the power 5 by 2 over v u to the power 3 by 2. Right? Now you see this quantity kappa is an arbitrary constant, and thermodynamics cannot give you any idea about this kappa. You have to go to statistical mechanics to determine what is going to be your kappa, right? So now what was S? It's a homogeneous function. So S was, if you recall, u by t minus p by tv minus mu by tn, right? But I know what is u by t. U by t has been given to me. U is 3 by 2 nkbt. So this becomes 3 by 2 nkb, PV by T is nkb, minus mu by T is nkb ln kappa n to the power 5 by 2 v2 e to the power 3 by 2. So I can take nkb outside. So I can just rearrange this to write down this as 5 by 2 nkb plus nkb ln v u to the power 3 by 2 kappa times n to the power 5 by 2, where I have now redefined the kappa. That's all. It's just a multiplicative constant. It doesn't matter whether it sits in the numerator or denominator. So I can do it like this, plus ln kappa v u to the power 3 by 2 over n to the power 5 by 2. You see, surprisingly, using the Gibbs, see how strong these equations are, how closely tight thermodynamics is, that I have now constructed the fundamental equation S as a function of UVN starting from these two equations. So from these two equations I have calculated mu, the third equation of state, and I have so mu over kBt, I have determined the third equation of state, and from there I have calculated the fundamental relation S of UVN. So most of the exercise in thermodynamics is essentially this, that either this relation is given to you and you look at all the thermodynamic processes starting from this equation. If you need the equation of state, you derive the equation of state from this equation. If you need to calculate the change of entropy, you can calculate the heat taken or given out, you can calculate this from this equation, right? Or the other way around is, if you are given the equations of state, either all of them, if all of them are given to you, then it is very, very trivial. You can just substitute this in the Gibbs-Duhem relation and you can find it out. So sometimes the equations of states were not given in the more easier form that you would prefer, but one has to do a little bit algebra to bring them to this form, to the form that you want essentially. And you can substitute this in the equation that we have just seen, the Euler relation for the entropy, and you can get the fundamental relations. If two equations are given to you and if the third is not given to you, then of course you can eliminate the other equation and you can determine the third equation of state from the Gibbs-Duhem relation and find out the fundamental relations.